So, in the next part of our course, we will be looking on a different topic which is known as VHDL. So, which is a hardware description language. So, the way that we have learnt in this particular course, we have seen that if you want to design a circuit, we have to start with logic gates and draw the circuit, and then to get a confidence on whether the circuit is working properly or not, we do some analysis of the circuit and try to see whether get the confidence that my design is correct. But if the circuit is very large, okay, so or if the design is very complex, then it is very difficult to do that type of approach. Like if you are trying to do a complex design, so there can be two ways in which we can do it. One is known as the top down approach, another is known as the bottom up approach. So, whatever we have learned so far, so we have learned about the bottom up approach. So, we can start with the simplest modules that we have in the design, and then we can after designing those and understanding that they are correct. So, we can go on connecting them in some fashion to get to connect to see that okay, if the complex functions are realized. Another approach that can be there is the top down approach, where we start with the topmost level of the design and then go on breaking them up and coming with the further and far simpler and simpler levels of implementations. Now, this this top down and bottom up approaches, so both of them, so they becomes complex when the overall design is quite complex, and in that way we need a better way to represent our design or our circuit. So, this VHDL is a hardware description language that will help us in doing that, and there are two such hardware description languages which are quite popular. One is this VHDL that we are going to discuss, and another is Verilog. So, both of them are equally powerful. So, there is no reason to believe that one is better than the others. It is just for an example that we have taken a VHDL. So, you can very well learn Verilog as Verilog language. So, we will be looking into a introduction of this VHDL language. So, this how does it work, what are the essential features of it. So, we will try to go look into it by means of an example. So, these hardware description languages, they come under the broad heading of HDLs, language to describe hardware. And so, this is why not the standard languages that we have in software like say C, C++, Java, Pascal, Fortran, etc. So, those languages, why they are not suitable for this hardware? The basic difference between the hardware and the software is that the hardware is always parallel in nature, whereas software is always sequential in nature. What I mean is like this, that if I write a program in say C language, and these are the several the statements of the C language, then these statements are executed one after the other. First this one is executed, then this one. So, it goes like this until and unless there is a branch. So, it goes in that sequence, and even if there is a branch, so it goes to the target, and then again from the target it goes sequentially. Whereas, in the hardware, so if I have got one functional modules here, another functional modules there, another functional module here like this. Now, all these functional modules, so they are always active. So, whether their outputs are meaningful to the user or not, that is a different question. Like if I have got one AND gate here and say one OR gate here, they are getting inputs. Now, maybe that their outputs will be say NANDed further to get the final output. So, whatever be the inputs here, this A, B, C, D values, so these gates are always working. So, these all the 3 gates, they are always working, but we are interested about the output of this NAND gate only when this one of these values of A, B, C, D have changed, and we are looking into this part. So, that way so that is the user's convenience. So, user finds that okay, I need to know the output at this point. So, that is the thing. Otherwise, if you look from this gates angle, then they are always doing the computation. So, there is nothing that it is there is nothing like sequential. It is not that this AND gate evaluates the output first, then this NAND gate, it is not like that. So, all of them are working together. It is only the point of sampling at which the user is interested about the output value, and that makes the difference. So, that is why this software languages, they are not suitable for hardware, because the software languages, they will not be able to capture the parallelism that you have in hardware. And similarly, hardware languages, they are not suitable for software, because hardware will assume that all the whatever you have described in that language, everything is in parallel. So, it will not be able to capture the inherent sequentialism that you need in case of software. So, coming back to the point, so we have got this hardware description language. So, there are two languages, one is known as VHDL, which is this V stands for this word V is stands for VHSIC. Okay, so, the VHSIC. So, which is very high speed. So, this is VHSIC, very high speed integrated circuits, then hardware description language. So, this VHSIC hardware description language or VHDL. So, it was developed by the Department of Defense from 1983, and IEEE standards have come up. Okay, so, it is based on the ADA language. So, the basic language on which this VHDL has been designed, so that is ADA. On the other hand, this Verilog is another standard language. So, that is again an IEEE standard has been defined, and it is based on C language. So, you can learn either of them. So, as I said that for this course we have taken up VHDL. So, why do we need this HDL? Okay. So, model and document digital systems. Actually, the point at which it started is like this. So, there are large amount of designs that were there, large number of circuits that were available, but the original designers are missing. So, original designers are not there. Now, how to understand? So, like if I draw a complex circuit, and if I am not available to explain it, so it is very difficult to understand the what is the motivation, how is this thing designed, and how to preserve this design, how to keep a note of the design content. So, that is the modeling and documentation of the digital system. So, it originally started with the documentation of the digital system. We have got a circuit. So, we want to make a document to describe the circuit. So, naturally you need to say that okay, these are the gates in my circuit, I am connecting it like this. So, this has to be done in some formal way. So, for documenting these digital systems, so we have to have this the HDL was necessary. Sometimes we need to model the behavior of a circuit. So, for that also this HDL is necessary, and this model, there are different level of abstraction. So, we have got this behavioral level, structural level, etc. So, you can describe a circuit in terms of its behavior. For example, if there is an adder, so you can simply say A equal to B plus C, that describes the behavior of the adder, or you can say that my circuit contains so many AND gate, OR gate, XOR gates, etc., and they are connected in this fashion. So, that also defines an adder only, but in a different way, that is the structural way of defining it. So, the same circuit we can have a behavioral description, we can have a structural description. Second objective is to verify the design. So, once you have got a description of the design, so you can try to verify the design by means of some sort of simulation, or maybe by means of some formal verification technique, you can try to extract the meaning of the description. So, when you do that, so you can get the meaning of it. So, that was another objective. So, this documentation was the first objective, modeling was the second objective, the third one is the verification of the design. And of course, verification may be of two type. So, when I say I want to verify, then there can be two approaches. One approach is via simulation. So, simulation means you have got a description of a system. Once I have described my circuit in terms of some language, and we also, so this is the description, and we have got some expected behavior of the circuit, and for that we design something called a stimulus. So, these are we define some certain stimulus, and we have got some expected behavior for each of these stimulus. So, we have got some expected behavior. Now, what you can do, you can try to apply the first stimulus onto the circuit and see whether it gives me the desired response or not. Then you apply the second stimulus and see whether it gives the desired response or not. For a combinational design, so you can apply this stimulus in any order. For a sequential design, so you have to apply them in a proper order only. So, whatever it is, so if I apply all these stimulus, then I am expecting that the response from the circuit will be like this only. So, if that thing happens, then I get the confidence that possibly my design is okay. Now, I say possibly because it is not possible, possible to enumerate all different situations that the circuit inputs can take, because that way the number of inputs that will be needed to be fed will be very high. For example, if there is a 10 input circuit, then if you are to apply, and a combinational circuit only, then if you are trying to apply all possible patterns, so it will be to power 10,024. So, that is manageable, but as the number of inputs becomes higher than say 30 or 40, so it becomes practically infeasible to apply all those patterns to the circuit and see the output. And that the situation is more complex when you have got sequential circuits, because then you have got even larger number of states that will come into picture. So, one type of verification is via this simulation. So, you apply some stimulus to the description and try to see whether that stimulus is sufficient for so the response is that you are getting from the circuit is as per your desired one. The other way of verification is by means of some formal method. So, this verification can be done by means of some formal methods, which come under the broad heading of formal verification. So, there you try to describe the behavior. So, if this is the description of the behavior, you try to describe this behavior in terms of some logic formula. You try to describe the behavior in some logic formula, and you also have the circuit in your hand. So, if this is the circuit that you have, so from the circuit also you can try to extract the logic formula and then try to establish an equivalency between these two logic formula. Okay. If these two logic formula they are equivalent to each other, that means this circuit realizes this description properly. If there is a gap, then it is not so. So, we can do this verification by means of this formal method also, but whatever we do, so we need a description of the system first. So, that is the another application area of this hardware description languages. The third one that has become more popular now, but it was initially not that way, is to synthesize the circuit. So, we start with a high level description of the circuit, and then from there we convert it into lower level of abstraction. So, high level of abstraction may be some language description of the circuit. That language description may be converted to say a module level description, like consisting of say adder, subtractor, registers, multipliers. Okay. So, like that. So, that can be converted into a next lower level, and that from that adder subtractor level description. So, we can again convert it into gate level description consisting of gates and flip flops. So, that gives the next level of abstraction. From there it can be further refined to transistor level description. So, that way we can go to lower and lower abstraction levels, and as we go there, so we can, and this process can be made automated. So, if we can automate that process, that means we have got a methodology to design a circuit from its specification. So, that is, so initially it was not the major goal of these languages, but now this has become one of the major goals. So, this simulation and this synthesis. So, these are the two major goals that we have from this HDL, that is for which this HDL is being used. So, next we will see like how can I specify a circuit. So, suppose this is a circuit. So, name of the circuit is my circuit. So, it has got 3 inputs A, B and S and 2 outputs X and Y. So, this example my circuit, it has got inputs A, B and C, and it has got outputs X and Y. So, when you are giving it a VHDL description, so we write it like this. So, this entire circuit, so this will be called an entity. So, in VHDL every module that you have will be called an entity. An entity will have some ports, okay, by which it can interact with the outside world, and accordingly we can it will be the behavior of this entity has to be described in either structurally or in a behavioral description. But this is the interface part. So, whenever you are defining the entity from the outside, how does it look like? So, one important part here is the port. Okay. So, it has got a few ports, this A, B, S, X and Y. So, these are the ports, and out of that A, B and S, they are input port and they are of type bit, and this X and Y, they are output port and they are also of type bit. So, you see a number of keywords in this description so far. This entity is a keyword, port is a keyword, then this in, out. So, these are keywords, and this bit, they are actually the data type or the signal type. So, ABC, you can say they are called, they are ABS, XY. So, they are signals. So, they are either input, output, or it can be bidirectional also. So, you can have this type as in out or mode as in out, and their type is bit. So, all of them are of type bit. So, we have got this. So, in this way you can define entities. So, this is the VHDL entity. Entity my circuit is port A, B, S, and these are input port and type bit, X and Y, they are output port of type bit. Okay. So, the things to be noted, this my circuit, it is the name of the circuit. So, every circuit should have entity should have a name. So, in a one description I can have only one name for a entity. So, and the names are unique. So, if there are multiple entities, so they should have different names, but these names are unique. So, this is user defined. So, these names user can give. So, file name same as circuit name. So, this is only recommended. So, this description in whatever file name you are writing. So, normally we write them in files having extension .v or .vhd, like that. Many tools, they will accept different types of extensions. So, for this case it may be the file name may be my circuit.vhd, circuit name is my circuit and the file name is my circuit.vhd, but this is just a suggestion or recommendation, but you may or may not follow it. Okay. So, that may or so we may or may not follow it. Now, next will be these are the port names A, B, S, X, Y. So, they are port names or signal names. So, they are the interfacing signals that you have. Again, the names here can be arbitrary. So, they can be chosen by the user, but again the same thing, that the same name cannot repeat. Okay. So, that restriction will be there. Then the next part is the direction part. So, this in and out, so they are directions. So, there can be three main direction types. One is in for the input, out for the output, and in out for the bidirectional. So, in out and in out. So, these are the bits. Okay. Then comes the data type. So, these are the data types. So, they are all of them are bit. So, there are some built in data type, just like any programming language you have got data types like say integer, character, boolean, real, like that. So, here also this VHDL language, it has got built in data types, like bit is a built in data type. There are other built in data types, they are like integer, byte, etc. they are there, but they can be there. I can have some user defined data type also. So, that is also possible. So, so as far as the syntax is concerned, there is a small observation that and on the last port we do not have the semicolon, the last signal we do not have the semicolon, and the semicolon is put at the end of the circuit description, the presence at the end of the closing bracket. So, this one, so you see that there has to be a semicolon here. So, though as if this semicolon is taken from here and put at the end of this closing bracket. So, this way we can define a VHDL entity. Next, we will be looking into the built in data types. So, first the scalar or single valued signal types, bit, boolean, integer. Okay. So, these are the different single valued signal types. Bit, they can be getting the value 0 or 1, boolean can be true or false, integer can be there will be some range. Okay. So, you can also tell the range of the integer. So, normally there can be unbounded integers. So, in that case the system will assume some bound. Otherwise, you can also tell the range of the integer. So, which is not possible in the software programming languages in most of the cases. So, we do not have this range available, but here we have got the range available. So, here we can say that A is an input port of type bit, G as an output of type boolean, and K is an output of type integer with the range minus 2 to the power 4 to 2 to the power 4 minus 1. So, it is basically 4 bit signed representation like that. Okay. So, these are the single valued things. For the aggregate one or the collection, so we have bit vector, because most of the times in the digital design, so we will be having connections, so which are arrays in nature. For example, if we are having this say CPU and memory, then we have got this address bus, data bus type of connections. So, we say this CPU and memory. So, we have got this address bus and data bus type of connection. So, these are maybe 16 bit, okay. Some other data bus may be 8 bit like that. So, this way there are a number of bits which are constituting each signal line. So, they are, so instead of treating them as individual bits, so it is better to treat them as a vector. So, that is the bit vector. So, we have got this bit vector as a a collection. So, array of bits representing binary numbers. So, that is bit vector. It can be signed. So, you can array of bits representing signed binary numbers, like say we have got D in bit vector 0 to 7. So, this is D is an input port where there are 8 lines and the lines are named as 0 to 7. So, D0 to D7 we have got 8 bits here. Similarly, E is input, it is again of type bit vector and 7 down to 0. So, so we have got E7 to 0. So, if you are assigning say if you are so the one is 2, another is down 2. So, if you are writing like say E assuming that E is output port. So, if you are write like say E should get the value D, then this D0 will come to E7 like that, because this is the MSB here is the so this is the MSB here, but in case of E down to 0. So, this is going to be the MSB. So, that way their values will be assigned properly. Then this 4 M in sign 4 down to 0. So, it is sign 5 bit 5 bit bit vector and it is a binary number. Okay. So, we can have different types of representations. Also, we can have the user defined data type. So, this construct we can construct data types arbitrarily or using built in data or by using built in data types. For example, we can say type temperature is high, medium, low, or type byte is array 0 to 7 of bit. So, we are defining two different types here. The first one is defining the type temperature. So, and its possible values are high, medium and low. So, the second one is defining a type called byte, and it says that this is an array 0 to 7 of bit. Okay. So, next if you say that I have got a signal x of type byte. So, this will mean that this is an array of bits 0 to 7, or if you have got say T of type temperature. So, it can take up the value high, medium and low. So, apparently it seems that this the user defined types. So, why are we introducing this other types like say temperature as a variable, temperature as a type, where these values are like this high, medium, low like that. So, in fact, if you look into this VHDL manual, you will find that it will allow you to define any user defined types. Okay. For even you can define the physical quantities like the size of a system, then its weight and all. So, which are not at all related to its electrical quantities, like say temperature of a body. So, that is not related to the electrical signals within that for that system. So, but still they can be described. So, while describing a physical system, so you may take help of those special types, special data types, and use them for your description. So, that actually makes the space the description complete, for the completeness of the description. So, you can use those things, though they are not synthesizable. For example, if you have got a type temperature high, low, medium, then there is no way by which I can do a synthesis of this temperature in my circuit. Okay. So, that is not possible, but still this strategy has been given this, so that we can define some physical quantities by means of this VHDL language. That makes VHDL really an exceptional one compared to other programming languages, where we do not have this type of features. Next, we will be looking into the functional specification. So, functional specification, like we can say that behavior for output x. So, we can say that when s equal to 0, x is assigned a, and when s equal to 1, x is assigned b. So, suppose this is the behavior of x, and behavior of y is when x equal to 0 and s equal to 0, then y is equal to 1, else y equal to 0. So, this may be the description of my circuit. So, behavior of x and y from the English language description of this my circuit, maybe we know that this should be the situation. Then when s is 0, then x will get a, when s is 1. So, there is a multiplexer here. So, between a and b. So, when and that select line is s, and then it is x, and if x is 0 and s equal to 0, then y is 1, otherwise y is 0. So, that way that is the description. So, how are you going to describe it in the VHDL? So, first one we will be looking into a sequential behavior. So, the any description of this VHDL is put into the VHDL architecture. So, for my circuit, the first thing that I have seen is the entity. So, entity has told the interface with the outside world, and then I am trying to describe what is there inside. So, for that I have to use this architecture part. So, this architecture keyword, it starts with the architecture keyword. Again, I can have several architectures of the same entity. So, for this entity, my circuit, I am defining an architecture, and this particular architecture name is say arc name. So, I can have another architecture also defined for my circuit. So, there is no restriction about how many architectures I am going to define for this entity, because this was more from the documentation point of view while initially designed, that is why it is like this. So, you can define one architecture from the behavioral side, another architecture from the structural side, like that. So, that is why I can have several architectures for the same entity. So, here we have got this architecture arc name of my circuit is, and then begin. So, these are all keywords, architecture, of, is, begin. Then this so, whenever you are trying to define something sequential, so you have to take help of this process block. Okay. So, this process so P1 is a process. Now, begin, if s equal to 0, then x equal to a, else x equal to b, end if x equal to 0 and s equal to 0, then y equal to 1, else y equal to 0, end if, then end process P1. So, this is the process description, and it depends, this process output depends on the signals A, B and S. So, they actually defines the values on which they are these process values are going to change. So, if there is a change in the values of A, B and S, then this description has to be followed to determine what are the values of x and y. So, that is what is done by this VHDL architecture block. So, there are some restrictions, like these signals defined as output ports can only be driven and not read. For example, so this x is defined as an output port, and I am trying to read the value of x here. So, but that is not possible, because that is an output from my entity. So, I cannot read it. So, in this way, from the it can catch many of these errors from the description itself. So, you see that these are some of the advantages that we have with VHDL. Okay. So, it can catch this type of design errors very easily. Otherwise, it physically means that from the output you are again drawing a line inside the circuit to check whether x equal to 0 or not. So, that is not a very good design practice. So, that has to be avoided.